Okay, so today we're diving into one of the most iconic pieces of military hardware out there, the Tomahawk cruise missile. But here's the thing, we're not just going to talk about it as a weapon. No, we're going to look at it as an absolute marvel of aeronautical engineering. So let's get right into what makes this thing, this flying robot, so incredibly special.
And look, it's a totally fair question. When you hear missile, you probably picture, a simple rocket just zipping from point A to point B. End of story. But the Tomahawk? It's something else entirely. Honestly, it's less of a missile and way more of a super sophisticated, semi-autonomous flying robot.
I mean, to really get why this thing is so special, you just have to look at what it can do. We're talking about a weapon that can fly for over 1,500 miles. And get this, it can do it skimming just 50 feet off the ground to stay hidden from radar. But here's the craziest part. It can get to its destination and just hang out. It can literally loiter, flying in circles for hours, which gives commanders this unbelievable flexibility. Oh, and it can be rerouted to a totally new target while it's already in the air. That is definitely not your average missile.
All right, let's kick this off by framing it the right way. We're dealing with a missile that thinks. This is a flying robot built for one thing: absolute precision. It's designed to find its own way through really complex environments, all to reach its target. So at its core, what is it? It's a subsonic cruise missile. Subsonic just means it flies slower than the speed of sound, and it's powered by a jet engine, kind of like a small airplane. And that's key because that's what gives it its incredible range and fuel efficiency. And where does it launch from? Well, it can be fired from surface ships like destroyers, or, and this is amazing, from submarines hidden deep underwater.
Okay, so what's actually packed inside one of these things? Let's pop the hood, so to speak, and deconstruct this modern marvel to see what really makes it tick. All right, let's look at the tail of the tape. It's about 20 feet long, weighs over 3,500 pounds, but the number that really jumps out at you is the speed. It cruises at nearly 580 miles per hour. To put that in perspective, that's basically the same speed as a commercial jetliner. And depending on what it's for, it can carry a massive conventional warhead or, back in the day, a W-80 nuclear payload.
Packed inside that sleek cylinder is a whole symphony of sophisticated tech, all working together perfectly. You've got the guidance systems. That's the brains of the whole operation. Then there's an infrared seeker for that final crucial approach to the target. And a satellite link so it can literally stay in touch with command. All of this is built around the warhead, the fuel tank, and, this is cool, 2 totally different engines. There's a super powerful solid fuel booster just for the launch, and then the main turbofan jet engine that takes over for the long haul.
So that leads to the next question, right? How does this thing actually get into the air and start its journey? Well, it's a really fascinating 2-stage process that's all about combining raw, brute force power with amazing efficiency. Okay, stage 1, the launch. This is pure, unadulterated brute force. A solid fuel rocket booster ignites, creating this immense blast of thrust that just shoots the missile straight up out of its launch tube. But that whole phase, it only lasts for about 10 seconds, just long enough to get it clear and give it momentum. Then, that booster just falls away, and the much, much more efficient turbofan jet engine kicks in to carry it the rest of the way, which, remember, could be over 1,500 miles. And check this out, here's another super clever piece of engineering. To save space inside that tight launch tube, the missile's wings and its control fins are all tucked in, completely folded up. But just seconds after it's airborne, pop! They extend out, transforming it from just a metal tube into a fully fledged, winged, self-guided vehicle ready for its mission.
Okay, this brings us to what is, for me, the most incredible part of the Tomahawk: its brain. I mean, think about it. How does a missile navigate through complex terrain, dodge obstacles, and find a super precise target hundreds and hundreds of miles away, all by itself?
Well, this gets right to the heart of a huge problem in missile guidance. You could just rely on GPS, right? But GPS alone only gets you to within about 30 feet of your target. And what happens if the enemy is jamming the GPS signal? The Tomahawk's solution is brilliant: redundancy. It adds multiple backup systems. We're talking TERCOM, DSMAC, and an infrared seeker, and all that technology together slashes the margin of error down to just 16 feet. That is some serious precision.
So that first layer of protection is something called TERCOM, which stands for Terrain Contour Matching. It's a really cool concept. As the missile flies low, a radar altimeter is constantly scanning the ground below it, basically creating a live 3D map of the hills and valleys. It then compares that live map to a preloaded map in its memory. If the bumps and dips line up, it knows it's exactly where it's supposed to be. It's almost like it's navigating by feeling the shape of the Earth.
Next up, you've got DSMAC, or digital scene matching. If TERCOM is navigating by touch, DSMAC is navigating by sight. As it gets closer to the target, a camera starts snapping pictures of the landscape. Then it compares those live pictures to satellite images it has stored in its memory, looking for specific landmarks, like a certain building or a bridge. When it gets a match, it can make these incredibly tiny course corrections to be even more accurate.
But here's the thing. Neither of those systems is perfect. TERCOM is pretty much useless over flat terrain, right? Like an ocean or a desert. There are no contours to match. In DSMAC, it can get confused by bad weather, like heavy rain or snow. So what's the solution? Engineers added one more layer, an imaging infrared seeker. This lets the missile literally see the heat signature of its target. That means it doesn't matter if it's day or night, clear or stormy. It provides that final, foolproof layer of precision.
Now, all this incredible technology didn't just appear out of nowhere. To really appreciate what the Tomahawk is today, you've got to look back at its legacy and see how it has evolved over the decades.
So the whole idea for this thing actually dates way back to the 1970s, and it officially entered service in 1983. And you can really see how its mission has changed. The original nuclear versions, they were retired after the Cold War ended. But the missile itself, it's been constantly upgraded year after year. Today, the advanced Block 4 and the brand new Block 5 versions are the real workhorses of the fleet.
And this is where it starts to sound like something straight out of science fiction. The modern Tomahawks have a two-way satellite link. Think about what that means. They can be redirected in the middle of a flight to one of 15 other pre-planned targets. They can do that loitering thing we talked about, just waiting for the command, and get this, they can even use their own sensors to send back a battle damage report to command after a strike. It's incredible.
Okay, but what does all this tech cost? Well, for all of this mind-bending capability, a single Tomahawk missile costs about $1.5 million. Now, I know what you're thinking. That sounds like a ton of money, and it is. But when you compare it to other cruise missiles out there, it's actually significantly cheaper. And that cost effectiveness is a massive strategic advantage. It's a powerful tool you can use without having to risk a pilot or a much, much more expensive aircraft.
And that really brings us to the final big picture thought here. The Tomahawk is a piece of technology that was born in the 1970s, yet here we are decades later, and it's still at the absolute cutting edge. Its journey, its constant evolution from a pretty basic guided missile into this networked, thinking, semi-autonomous robot, it really makes you wonder, right? What does that tell us about the future of smart technology? Not just in the military, but in every single part of our lives.